problem that looks like this, then we alluded to this last time that maybe what we could do is we could draw our little box like this, and we'd have flow from the upstream side to the downstream side. The reason that this is kind of stippled here and not on the upstream is that there's some dissolved product which comes out of here which gets carried downstream. And it has two effects. One is that it makes the water not very good downstream, it contaminates it at some relatively low concentration. But also, because it's physically taking mass from this chimney and taking it downstream, it's also depleting it, right? It's physically removing it. And so assignment 4 is basically doing the calculation. If you had a geometry that looked like this, and well, I guess I could pull up assignment 4, right? So where is it? I'm not online, but I can actually do it from the website. Should get a new picture one of these days. It's a bit old. Not a bit, yeah, a bit old. Yeah. Where is it? And so the geometry is this. And so the idea is that instead of having it horizontally, chimney, flow from left to right, make life easy, and you just have the same geometry, if you like, on its tilted on its side. This kind of relative permeability curve, just drawn like this for no particular reason, has to go through these ordinates of 1 and 0 and does something in the middle. This is slightly different, you see, just out of choice, but you should be able to use that, for instance, in this case, to be able to figure out exactly, one, what is the flow rate of water that you get through there. Presumably, depending on the saturation that you have here, there would be some water flow through there, right? And if you were, for instance, if the NAPL concentration was really high, and this is where you were, then you would get essentially no water going through there. This is relatively curved water. If you put a straw in it, you suck out the NAPL. Conversely, if we don't know these chimneys, but take it on trust that these chimneys are kind of a smear zone. It keeps some stuff back, it attaches there, and the main plug goes keep on going down until it hits the water table. And so this smear zone means that the saturation of the gasoline perhaps is 5 or 10% on average, and so you're over here. And so you actually basically have the relative permeability of the water, which is almost 100%. You can't remove the other material there just because it's sitting there, and the only way it will be removed is being dissolved in the water and being carried out. And of course, if the saturation was something in between, then you'd actually have a saturation of the water, which is here, and the rel term of the water would be 0.95. And as you slowly dissolve this stuff from the plug that's in there, then you'd physically be mounting up this curve here, and then moving towards 100% water because it'd be dissolved. So we said you can't get it out by physically displacing it as free product. The bubbles of this stuff that sit on the grains, you'll never be able to get out because you'll put a pressure across it, and the pressure will short circuit from water to water, and it won't have any pull whatsoever on the NAPL that's sitting in there. But you will dissolve it, and by dissolving it, you'll slowly move across this. Yeah.
So on that curve, what's the difference between X curve and one with like the actual?
The actual one is, well, the actual one is the actual one. So typically what they do look like is, they look like, often, like this, where this amount is lower than this one because of the different pores that get saturated. But these are so difficult to define that you could make an assumption that it looks somewhat simpler. So X curve is just a simplification. In the same way that in lots of the calculations we've done, we've only cared about this entry pressure, we haven't cared about the rest of the curve. And if you know this entry pressure, you can say lots of things about it, unfortunately. So this is friction, if you like, the X curve, a convenience, and this is reality, but you don't often know reality. And the other thing that comes up for conversations with you is that typically permeabilities, actual permeabilities, change from Yucca Mountain rocks, which are 10 to the minus 18, so a microdarcy, to maybe 10 to the minus 12, which is a darcy. It's kind of a sand. And so there's six orders of magnitude changing there. And so if you're using a factor of 2 here in a calculation, or a factor of 3, actually it often comes out in the wash, because the other parameters that are so ill-defined and cover such a broad spectrum of parameter ranges. So that's the other thing which I think you're not used to doing, is making assumptions and trying to feel comfortable with them and then justifying them. And ultimately, in your professional life, you'll be doing those things and you'll be standing up and defending those kinds of things in front of judges and courts and townships and other colleagues, etc. And so you should get used to being able to make order of magnitude estimates for these things. So to solve this problem, the way to do it would be to follow the response of how permeability would change. And so I guess if I didn't open it in the right point, but in this case, I think the question is, you start off at some saturation, can't see it right now, I'm looking for it. NAPL saturation is 10%. So in this case, if you start off at 10%, I can't mark it on here, but it'd be right here. And so you could calculate the flow you'd get through this system as a function of this particular geometry. As you start removing material, you'll reduce the amount of stuff which is there at some mass removal rate. And as you change that mass removal rate, you'll go up on the curve. The reality is, of course, is that if you start off at 10% NAPL, and therefore on this curve you're basically 90% relative permeability, then actually the change from 90% permeability to 100% permeability is almost inconsequential. So you could actually do the calculations probably with an average of 95% and just figure out what the mass removal rate is. So you should make assumptions and simplifications that you think you can justify, and justify them, and they'll probably be reasonable. And so if we're doing that behavior, then this stuff is in your notes. This exactly does that. And so this is the same kind of experiment. This is this NAPL plug that sits here. It happens to be, you might not be able to see it very well, but it starts off at 17% NAPL saturation. And this is just the modeling results that follow this behavior. And so if we look at those modeling results, they are just modeling results. They should make some kind of broad sense. It's a sand aquifer. We'll use the Borden aquifer. It's an experimental field site in Ontario, which has been used over the last 20 years or so and still is in use. But basically, this is the geometry that we're looking at on the top here. This NAPL plug, you flow stuff through it, you get a plume that goes downstream. It removes mass at some mass removal rate, whatever that is. You have a relative permeability curve. You start off at some relative perm, and you change over time as you start removing it. So what would we expect the behavior to look like? And so these plots are plots of a model of that exact process. So I don't know whether you can see these very well. They're not fantastic resolution or anything like that, but they do make the point. So this is the upstream part of the core, downstream part of the core, 2 meters long. Concentration of 1, relative concentration of 1, concentration of 0. Upstream of the plume, upstream of the NAPL would be nothing, right? Except for maybe something by diffusion a little ahead of it. As you start pumping water through it, then you raise the concentration from the initial value here progressively to some steady state value after 3 days. This is basically saying that after 3 days, fresh water comes in here. At this point, it's still fresh. It takes some time to have the mass transfer into it, some kind of kinetic effect. And as it goes across this NAPL zone, it takes a certain amount of time to fully reach its full concentration. And then once it has that concentration, it carries that downstream. So this curve that I've done in red is just a snapshot at time. So it's 100% dissolved concentration downstream, and it rises up to 100% as it goes across this zone. And then progressively after 3 days, so this is early time, slightly later time, later time, later time, 3 days. If you look then from 3 days onwards, then you start off from this same behavior you had on the left-hand plot, but then after it's reached this steady state, because you're physically removing mass from here, at least from the upstream edge, then slowly over time the concentration starts to reduce because there's not so much there anymore as there was before. And so it doesn't get up to the same concentration by the time it's got to the other side of this zone, and slowly at very late time this concentration starts to deplete, so after 100 days the actual concentration coming out of the downstream side is much lower. And so hopefully that makes some sense.
If you wanted to do this as a much simpler calculation, you just calculate what the flow rate is through this thing here, and you could calculate, of course, the flow rate would be what? The fluid flow rate would be the cross-sectional area, the relative perm, humerus, the absolute perm, the head drop across the system, and the unit weight of water. Right? You'd have that. And if you want to calculate the rate at which you would remove mass from this, it's going to be equal to the volumetric flow rate times the concentration, which is volume per unit time. Concentration is mass, usually milligrams, but just use kilograms per volume of water. So milligrams of TCE per liter, for instance, would be per liter of water. So if you want to do a back of the envelope calculation, quote unquote, then those are the expressions that you'd use. And you'd probably, if you use the same parameters, hopefully you'd find out that after 100 days, you've basically depleted the amount that's sitting in here that you could count. What else will happen as you do this? So this is concentration versus downstream length. This is relative permeability versus downstream length. So where there's nothing there, the relative permeability to water is going to be 100%, 1.0. When there's nothing that's free product downstream, it's going to be 100%, which is 1.0. But as you raise the, as you start removing the material from this, then it starts off at some uniform relative permeability. So this is 1, 0.9, 0.8, 0.7, 0.6, 0.5, 0.3. So it starts off at some magnitude after 3 days because it's part of the pore space is occluded. And once you start to remove the material by reducing this, because the concentration is going down in here, it's going down because you've actually removed some of the material by dissolving it and taking it downstream, so it's no longer filling up the pore space, so you'd expect the relative perms to go up. And so after 100 days, the relative perm is almost 100%. So this is, after 100 days, it looks like this. And so that's not going to make any difference on the flow across that. And this would be the saturation of the components within the chimney, if you like, this partially saturated zone where there's NAPL. So what do you expect? So at 3 days, it has the highest saturation that it started with, and as you go on, the saturation gets less and less, and you remove it, and therefore the relative perm to water goes up. And so that's exactly what you think. You start off with some saturation, which is relatively high. I think it started off at, in this case, at 17% saturation. I think this is 0.2. And as you dissolve it, by the time you get down to 100 days, the saturation of the free phase within the pore space is almost gone because it's all been dissolved and carried downstream. And so you can use the kinds of calculations that we've talked about to be able to do that. What else would make sense if you looked at the behavior across this system? Well, what do you expect the head profile to look like as you went from the upstream to the downstream? So you have an upstream magnitude of pressure or head, you have a downstream magnitude of pressure or head. If it was a uniform permeability, what would the head distribution look like? I'm guessing the answer isn't on your phone. Straight line. Someone said a straight line. Exactly right. If you have a low permeability region in the middle, how do you think it would deviate from a straight line? Right. This is the core. This is the upstream head, which is 1. This is downstream location. This is downstream location. So how would you rationalize what it would look like? What do you think? how do you rationalize what it would look like? You know, for instance, that the, whoops, the cable's on there, can't write the cable. So you could rationalize it because you know that Darcy's law is equal to something like, let's just write effective permeability over viscosity of water times dH dx. You know from continuity that the flow velocity here has to be the same as the flow velocity here and the same as the flow velocity here, right? Because it's the same as traffic down the road. If one car is going faster than the other, then it physically accumulates. You catch up on the other material. But if you're in steady state, then the flow rate here has to be just the same as this, otherwise you'll get some accumulation of fluid in the system. And so the velocity at all of these locations, V1 and V2 and V3, have to be the same. And so if this is the same for all of these regions, if you decrease the permeability, what you have to do to the gradient to keep up. Yeah, you got it. And so in this region, if the permeability is lower, then you've got to have, instead of this gradient, you've got to have a gradient that is steeper. And so I think you'd expect it to look like this. These are supposed to be straight lines on these other parts. But they're not quite straight, I know. We're not all perfect. And so that's exactly what you see here. So initially when you start off with NAPL in this region here, this is this NAPL region, the head distribution is small in the high permeability. The gradient is small in the high permeability region. It's steep in the low permeability region. And then it's shallow again in the high permeability region. And then as it washes out the NAPL that's here, the permeability in this region goes to be exactly the same as the stuff on either side. And you expect that therefore this should be a straight line. So this one comes down slightly, this one goes up slightly, and the final distribution is a straight line that just goes through these, which I can't draw very well. But you get the idea. So I have to rationalize it. So what we're doing is trying to synthesize the things that we've talked about to see that they make some amount of sense. You can change the magnitudes of all these different things, and of course the ultimate behavior that you might want to look at as a result of these is if you have, for instance, the concentration and how that concentration changes along the length of this core, then typically what we're thinking of this as an analog to is you have this region which is NAPL, water's flowing horizontally from upstream to downstream. This is where you live, this is where your well is, and you're taking water out. The water that you take out is at this particular concentration, and so it may be that we're interested in whatever the concentration is at this point and how it changes with time. And of course that is exactly what this plot is here, and I can't necessarily remember what all these components are, but these would be cases where you have lambda is a mass transfer coefficient, so where lambda is large, you get transfer from the free phase into the dissolved phase quickly, and so you start off with high concentrations as you go across this region because it's able to transfer from the non-aqueous phase into the water very efficiently, and so therefore you get a high concentration initially, but because you have a high concentration going into it, it's depleting quickly as well, and so it falls off to some background to zero concentration quite quickly. In the cases where the mass transfer coefficient is smaller, which are these values here, this is mass transfer coefficient here, which we don't know what this mass transfer coefficient is yet because we haven't talked about it, then as the water goes across this NAPL zone, it's going too quickly to be able to pick up its full loading, if you like, of NAPL. It doesn't reach the saturation, the chemical saturation, the maximum solubility, if you like, that it would be if you put this NAPL in water and left it there, it reached some maximum solubility. In this case, it's scooting across that zone so quickly that it can't pick up its full loading, and so when it comes out of the downstream side of the NAPL chimney, it's not very high. It's not a relative concentration of the solubility, but it's some fraction of that, 40%. So that means it's coming out at a lower concentration, which might be good, but because it's coming out at a lower concentration, it takes longer to physically remove that given mass out of the system, and so the tail off to zero concentration takes longer, which is obviously exactly logical. I'm not sure if you're allowed to ask questions, Taha, but I guess you could. Yeah, go.
Are we talking about the same head weighting that is there, like the hydraulic weighting?
Yeah, yeah. So I'm thinking.
But the only thing that is changing is the mass transfer rate that you're talking about. Right?
Well, it is in those, but there's something else. I'm trying to think what this is. No, I guess the head's changing in this particular. This is a higher. It's either a length of the core or it's the head. Yeah. So this is a higher head. So see if that makes sense. So in the case where the mass transfer coefficient is high and it travels through it, I think that's this one here, right? So this is this. And the same mass transfer coefficient, but a...
The lower one, right? 60 mm.
Yeah, so this, yeah, but this, so isn't that backward? No, it's not. Okay, no, it's not backwards, right? So this is the fastest flow rate, and so yeah, but if that's the gradient, it's backwards, right? So if you have the same mass transfer coefficient, they're the same magnitudes, but if it's flowing at a head of 60 centimeters, it would be physically flowing faster, so it would deplete faster, and therefore this one should go down before this one, right? So it can't be head, so that's backwards. And so I'm trying to think what the res is. Is it residual? Don't know. But anyway, so.
Is it the length of the residual then?
Could be, yeah. Instead of 30, yeah, you're right, yeah. So 60, yeah, right. So 60 centimeters versus 30 centimeters, yeah, excellent. And so if that's the case, does that make sense? So now so they're flowing at the same flow rates, so they should be, and the same mass transfer coefficient, so they should be the same concentrations. The one which has the longer zone will have more mass, and so it should endure longer. And so it does, yeah, okay. That's exactly what it is. Thanks. Good. Well, working in real time here. Collaborative learning, they tell me. And so where the mass transfer coefficients are larger, then it should have a lower concentration. And maybe the difference between these two are the same mass transfer coefficients, this and this. So in this case, not only is it, so the relative permeability is making it go through slower, I guess. So it reaches, no, faster in this case, and so it reaches a lower concentration, yeah. Less long zone, so overall the impedance is going to be smaller, goes through faster. If it goes through faster, then in some cases it won't reach even the same concentration as before, and because the residual zone is less long, it also dies out earlier because there's less mass in there. So, yeah. So anyway, so just to get a general feel. So you can't do this calculation with what you know so far, but you could certainly do a surrogate calculation based on the understanding that you have on relative perms. Okay, all right? All right, everyone okay with that? Good. All right, so that's the recap, I suppose. What I wanted to talk about was movement of NAPLs, and I was going to use as the notes, I made notes in my own notes, that the only pages I'd look at were going to be, the other's narrative, but these are the pages I'm going to go to, and just describe, they're mainly graphical figures to describe these behaviors, so you can have that as well as I do. So for what it's worth, that's what we'll talk about. Okay, so we know that our interest is in being able to understand this behavior. And so we have the tools now to be able to understand something about what the distributions of saturations and relative permeabilities would be in this this zone, both for LNAPLs, these are DNAPLs, right, of course. They've gone across the water table and only been stopped by what's called here an aquitard, but we know that that's a non sequitur, right, or a misnomer, is that it's really a capillary barrier. But capillary behavior tends to be related to permeability response as well, as we know. Okay, so page 73. Not going to care about this. This basically says that if you have NAPL in groundwater, you can calculate the body force that flowing water would apply on that, and it turns out that the body force that you apply is so incredibly trivial that you'll never ever move it. And the only way that you'll move it and change the saturations when it's close to these very low saturations of maybe 30, 20, 10% saturation of NAPL, the only way you'll do it is by dissolving it. And so that's what this page talks about, and this page. So is this 73? Okay. So I'm skipping around. So what do we know about in terms of pragmatics of what we'd like to say about these zones? So the first one is to talk about LNAPLs, those that float on the water table. And so we've looked at this figure in the past that divides our vadose zone into something which, by definition, the water table is where the water pressure is atmospheric, and where it's not only is it saturated, but we know that because of this diagram here, that we're certainly 100% saturated here, and also here, and also here, and also here. So in other words, this would be the water table, where the pressure is 0 for atmospheric pressure. And as you go up here, there's a zone which is sometimes referred to as the capillary fringe or the tension saturated zone, because it's almost fully saturated because of the interfacial tension of water, which sucks it in there. And so if you look at the saturation along there, we have a zone which is 100% water saturated, basically. It may have a small portion of residual air in it as well, depending on the pathway that we took. And we talked about different kinds of saturations, saturated zones. One which was funicular saturation, one was pendular saturation. I don't know if you remember. Pendular saturation meant that the water, if you like, at grain-to-grain contacts was a donut that was the cushion, if you like, between the two grains, surrounding the contour of these, and like a pendant zone that was a pendant around the two grain contacts. And a funicular zone was where you have a bubble of air that might be completely surrounded by water, and the water is present within the pore space. So I don't know if I can draw that. So if you want to remember exactly what this was like, then the funicular zone would be where the white around here is the water, and in here you'd have a little blob of air or NAPL, depending on what the other phase is. And the idea is the same as with a funicular railway. The only way you can move that is by pulling water through this system and dragging this bubble with it. And typically the pore throat sizes are too large to allow that to happen. Pendular zone just referred to the fact that on two grain-to-grain contacts, that like this, then the pendular zone was a portion of water, if you can see it, not very well drawn. I wish one of these days I'll work out how to use different colors on this. It's not easy to change. I try and change them, it never changes. But the pendular zone, this pendant of water, is just this red area which exists on the edge of these grains. And so you can imagine that this is a grain, pointing like this. There's a ring that cushions them, and in addition to that, there's actually a monolayer of water that covers all of these grains, because of course this water loves to be in contact with quartz if it's a wetting solid, a wetting fluid rather. All right? And so we know that as you go up in the vadose zone, if you can calculate how the capillary pressure changes with height, and you know what the capillary pressure is at a particular location, then immediately you can calculate what the saturation of water would be, which would be this, and the saturation of the other non-wetting fluid would be which would be this. Those two lengths. Non-wetting fluid might be air, as in the vadose zone for soil physicists. It might be invaded by NAPL, or gasoline or whatever, for the case of that we're interested in. These are all taken from Feder. I guess if you've looked at Feder, you'd certainly realize that. So I'd encourage you to read this chapter. The other kind of counterintuitive behavior is that if you look at fine-grained materials compared to coarse-grained materials, the height rise of water, the capillary fringe in fine-grained materials is much higher than in gravels. It makes sense, right? Because we know that this value of the height rise is proportional to the interfacial tension and the diameter of the pores. So if the pore diameter is really small, then this height rise in the columns is going to be very big. And so this table is basically saying that. And so you counterintuitively, low permeability materials have a big capillary fringe in them because they're able to keep the water in there. And actually, I'm not sure that we ever talked about it in much detail, and I'm kind of diverging, I guess. But if you look at Yucca Mountain, which is, I think, a classic example of a really fine-grained material, which you've been playing around with. These are the data you had. I can't remember whether you had this. Certainly you had this figure, and you had this figure for your assignment. But this is a plot of the capillary pressure. So water potential is the soil physicist's name for capillary pressure. Same thing. Yucca Mountain, the water table is, I think, at 600 meters below the surface, so that's about 1,800 feet. This is the ground surface here. And it's looks like a shotgun blast, but perhaps you can't see very well. This is a log scale for water potential. And these actual dots are the magnitudes of the capillary pressure that's measured within the water, within the matrix in the whole column at Yucca Mountain. And you see that the water potential is actually negative capillary pressure. So these are in tension. And so there's 10 atmospheres of pressure in the water, in tension, in the pore space in the rocks. It happens to be plotted against a log scale, so it's not very obvious. But if you plotted this height, vertical height on this scale, this is the repository or the previously proposed repository at 350 meters, and you plotted that against water pressure, you'd actually just get a line that looked like this. And this water pressure is just the unit weight of water multiplied by the height above the water table. And it's the height rise. It's the same as this height, this column of stuff in the matrix, not in the fractures. Fractures are much more open. But in the matrix, it rises up to almost 100 times the atmospheric pressure. So atmospheric pressure is 0.1 of an MPa. So 10 times is 1 megapascal. This is 10 megapascals. A meter of water is equal to what? How many meters of water is that? So what did I say? 100 times 0.1 is 10 megapascals. How many meters of water is that as you go up? 10 megapascals is how many meters of water? How deep in a swimming pool do you have to go to get to 10 megapascals? Unit weight of water is about 10 kilopascals. So 10 megapascals is 1,000 times that. So it's 1,000 meters. And so basically if it's 1,000 meters, you don't quite get there, it would be 1,000 meters of water head, negative water head. So in other words, this is actually about 600 meters. So I guess we don't actually go up to 1,000. So it's like standing on the surface and having a pipe that you hold on to, and that pipe is filled all the way down to 600 meters below you where it hits the water table, and you're physically picking that pipe up. And it's the stress that you have to apply per unit area of that pipe to be able to pick it up. You're basically taking a capillary tube. You know, the analysis we did was to take a capillary tube which looked like this. A very narrow tube will have a height rise in it, which is h sub c. We said by definition that this is atmospheric pressure if it's just stuck into water. This is almost also atmospheric pressure. So basically you can cut this off, and the free body diagram is that you're applying a force here and a force here to be able to physically pick this up. That's basically what you're doing. And so it's the same thing, that the force that you're applying, the stress you're applying at the surface here is basically the water column, which is 600 meters tall. So they're incredibly negative and very high pressures which are present, which you might not expect, but it's because it's very low permeability material, which has very small pore sizes, which can therefore sustain those pressures. Okay. So I'm diverging, right? Not getting where we are. So, all right, so coming back to this. So this is, again, in Fetter, so you can go and read up on it after the fact. If you start off with the pressure, the saturation versus elevation, so this is also kind of a proxy for capillary pressure, right? Negative capillary pressure as you go up through the section. If you spill some NAPL in here, so if you spill gasoline in here, which of course is lighter than water, what would it do? Well, looking at these are the progression of this after 2 hours, I guess after 8 hours, and then final behavior is that after 2 hours, this is the water table. And coming down on this water table, you have this tongue of this invading fluid. So this is the saturation, if you like, or the water content. Remember we said something, how did we define water content before? It's the way that soil physicists define volumes of stuff in pore spaces. The moisture content is equal to saturation times porosity. Right? So the porosity of this stuff must be 32%, 34%. So this must be the porosity in this particular case. So just another way of representing saturations. And so what? This is the amount of oil in the system at that particular depth. This is the amount of water, I guess the volumetric water content, which is what in this case? It's about, this is 0.2, 0.1, this is 0.01 maybe. What's this length here? Well, I'm guessing it's between here and here, so it's about 0.15. The volumetric content of the non-wetting fluid is equal to 0.15, say, at that particular height. And at this place, of course, there's none. This is as far as it's reached. And of course, the remainder of this is what? What's the remaining fluid in here? Yeah, air. Whoops, stay there. So you have those three phases in this. You wait a bit longer. You take a line across here, and you have this. Again, this is air. This is non-wetting, and this is water. And so this, of course, looks kind of a little bit like our chimney, right? So there's maybe a small saturation of non-wetting fluid, there's a little bit of water that's left, and a whole lot of air in this system. And so physically what that would represent in the systems we're dealing with, it would be something, it would be here, right? So this would be NAPL in this zone, there'd be a whole bunch of air, there'd be a little bit of water because we have the water table, and this is lighter than water, and so it can't get down below here because it can't physically push, doesn't have its weight to be able to push below there. And so after some time, after everything settles, then the behavior that we'd be interested in is this. Go across here. It's not very horizontal, but try and get it all the way through here. So this is now the amount which is in the non-wetting fluid. This is the amount which is in air, and this is the amount which is in water. And so if you drew our little kind of cartoon of what this looks like, I think it looks like this. Oh my God, all kinds of stuff going around. And here too. So this is the water table, right? So by definition, this is physically what it looks like. As you go across here, this is almost fully saturated with this non-wetting fluid. As you go up through here, then it's, you just take another section. There's a little bit of residual stuff, which is this chimney, kind of can't do it very well. A little bit of water, which hasn't really changed, which is just held as this pendular saturation between the grains, and a whole lot of air, which is present. Right in here. And so this is the, if you like, our representation in a quantitative way of the cartoon that we've had to represent this behavior that we've talked about many times. And so that's really all we're attempting to do. So the narrative of being able to deal with this, I guess, is that if you put a straw in here, you'd basically suck out a lot of air and a bit of vapor because you'd volatilize it as you took it out. If you put a straw in here, then initially you'd be able to suck out a bunch of the free product, the gasoline if you like, and then as you reduce the saturation of this, all of a sudden there'd be a bunch of water in there, and you'd just be pulling out water or air depending on where you are. The other thing that you notice is that the water table, or the tension saturated zone, was originally up to about 30 centimeters above the water table. And if you look at 30 centimeters above the water table now, it's kind of this line here. So the other thing that it's done is it's physically depressed the water table, because instead of having air sitting on top of it, you actually have this other gasoline that's kind of depressed it. And so this has actually pushed down the water table a little bit where it exists. Probably not a very significant component, but merely the fact that the original tension saturated zone was about 30 centimeters before, and now if you look at 30 centimeters, everything below 30 centimeters has now got this lens, this NAPL lens. If you looked, so it's exactly this, right? This is the zone where we have it saturated, this lens. Above here we have this chimney, which is partially very low saturation of the NAPL, almost 100% saturated with NAPL, but 80% saturated with NAPL. And below this it's all water, but this plume now is just dissolved in water. So maybe this is 20% of the pore space is filled with NAPL, maybe 80% of the pore space is filled with NAPL, and it looks like this. And in this, there's no free product in here whatsoever. So the saturation of the non-wetting fluid is equal to 0, but the concentration of this is maybe 10, 50, 100, 1,000 parts per million dissolved in water. Not present as a free product, but dissolved in water. And so that's what we'll talk about when we'll talk about contaminant transport, which is what we haven't done yet. If you follow those same figures that we talked about here for time 0, 120 minutes, 480 minutes, and ultimately, and you looked at the pressures that you measured within the soil column, then you'd get something like this, I think, for the same ones. Although, confusingly, this is again out of Feder, this is at 120, this is 0 rather, this is 120, I think this is 480, and this is infinity time. And these are the pressures. So the pressures are at the water table, by definition, the capillary pressure, or the pressure in the fluid in the water, is 0. As you go below that, it just increases as like going down in the swimming pool. As you go above it, it increases on exactly the same trajectory, at least the pressure in the water. This is why it's called tension saturated zone, because it's in tension. It's less than atmospheric, but it's not less than absolute pressure, right? If it's absolute pressure, if the absolute pressure of this is 0, then it cavitates. It becomes a vapor, or slightly below. As you add this tongue of fluid, then what happens is you see that this water table here, which was the atmospheric pressure point, physically moves up. So the pressures have changed now to look like this. This has moved the water table up to this point here. And this is the pressure in the oil as you go down here. And there's just this little jog. As you keep on adding more, as it keeps on migrating downwards, then it changes the fluid pressures until you get this final disposition of behavior. And so these would actually be the pressures that you'd measure. And so from these pressures, you can surmise what the behavior would be, right? So this is the pressure in the water, in the fluid. And so by definition, where this hits atmospheric pressure is the water table, by definition. But as you go above this, then all of a sudden, there's a higher pressure above this, which is due to the NAPL that sits above this. And as you go up in the NAPL, which is the predominant fluid, now you hit another region where you're also at zero pressure as well. And so this would be the oil table. And so if you think about it, this oil table here is where the uppermost extent of this, all the pores being largely filled with oil is, and it's right here. And the uppermost extent of where the water is at atmospheric pressure is below this region. So you have this kind of lens here, right? I always draw it like this. This top is really quite flat, I think, but this is oil. This is kind of the oil table that sits on top. This is the water table that sits underneath. And it's given by these points. And it's absolutely logical and rational, of course, because by definition, the water table is where the pressure is atmospheric. And this is atmospheric in water. This is atmospheric in oil. And so it's just... So both this sequence of figures and these sequence of figures are saying in kind of a quantitative way, relative to what's on the board, exactly what the profiles of pressure and saturations would look like as you go down through this. And that's important because what you might want to do is put a straw down in here and suck this stuff out. And you'd like to know when you can do that and how much you might want to be able to pull out. And so you can do that now with your knowledge of capillary pressure versus saturation curves. I won't talk about the... I'll let you read about the dissolved components. Your second assignment, once you get this one in today, will come live, or the third assignment, I guess, rather. Here's your bargain. Don't do part 2. Just do part 1. Part 2 is about dissolved components. It's a bit confusing because it's earlier than we've dealt with it. So just do part 1 for now. You'll get practice to do the equivalent of part 2, question 2 later. Okay? Unless, of course, you've done it, then you should hand it in. All right, so if we think we can... So based on what we've said already about these distributions of NAPL and water in the subsurface, what we might want to know is if we try sucking this stuff out, how much is going to come out, and how do we know when we're done? And so we know that there's kind of a water table and an oil table, and physically they would look a bit like this. And when we drill a hole to be able to look at this, one question would be, if you drill a hole through this and you look at in the walls of this hole exactly what is present at these different locations, would you see that there's oil present here, water present here, and air present here, or would you see something else? So that's one question. And so let's think a little bit about that. So what this has suggested is that if you drill a hole through this lens of free product that sits here, then we won't necessarily, in the hole, we don't really look at what's in the walls of this material, which might actually give us the correct answer. But typically what we do is we look at what's present in the hole. And what's present in the hole is a column of water to some depth, and above this will be a column of floating product. And so I guess the question is whether this column of gasoline that sits in here, this green stuff, would be coincident with this thickness of this lens that sits there. And so that's a fundamental question that we should ask ourselves. And the answer, as you might surmise from this kind of cartoon, is no, it's not the same. And so how do we correct to be able to figure out exactly what the true thickness of this free product is as a function of the actual thickness of this that we will measure in the hole? And we'll measure it. So in 452, when you measured, did you ever go out into the field to do any of this stuff? Did you ever go out to the well field? Penn State well field? No? Did you ever use a water level indicator? No? Okay. Well, so if you have a well bore, one thing that you can do is you can drop, so you don't know how deep the water is, but you might want to know where that is. So one thing you can do is you can just drop a probe down it. Probe comes on a piece of electrical tape, so it's actually just a piece of tape, basically. It has a conductor down one side, another conductor down the other side. They join in this little probe that's here, and they join, I can't really draw it. No, it's basically, if you look at what the probe is at the base of it, it's you have a circuit, you have a battery on the surface with a light bulb in circuit. You have the two cables that go down the well into this probe, and the probe has two open terminals. When the probe hits water, whoops, you make the circuit. When the circuit's made, the light comes on, and you know whatever the length of cable you have down here, you've hit the water table. And so these little probes are just that. There's a little hole, this tip here hits the water. You measure how deep the probe is, and you know the water is at 10 meters depth. You can also get these probes that they'll go not only sense the interface between the water and the NAPL, but they'll also sense the interface between the DNAPL and air, because they're different resistivities. And so you can basically locate what the depths of this free product in the wellbore here is both the air interface and also the water interface. And so the question is, if this interface is going to be different from what's present in the aquifer, then how do we make that correction? How do we rationalize it? And so in the borehole, we don't have any capillarity acting. So if you fill the borehole with water, then the pressures that you get here will actually be in some kind of equilibrium with the fluid pressure within the fluid here. And so what we know is that we have a water table, which is this kind of upper blue part here, and we have an oil table, which is this upper part here. So what we could do is we could use that information to be able to figure out exactly what the mismatch between this measured height in the borehole, which we can measure by one of these probes, which will be a thickness T, and what the actual thickness of this is, which we really don't know, but we'd like to know. So it's a correction, if you like. And so the calculation is pretty straightforward. And it is that we know that as you go down in this wellbore, the pressure at this place is atmospheric. As you go down to this interface, then the pressure increase with depth is going to be equal to what? The pressure is going to be equal to the depth below the surface times the unit weight of the non-wetting fluid, which I guess in this case we've called, I've covered it up, I guess is gasoline, G for gasoline. And so you can calculate what the pressure would be at this point. You know that the water immediately underneath this has to be exactly the same pressure at this point here, which is at some depth here. But you know that also the pressure here has to be atmospheric as well. And so you could also go down in the water, and as you go down in the water some depth, then the pressure drop as you go down here to this particular point, which is this interface here, has to be equal to this pressure minus, this is, I guess, W, I've called it. And so this pressure change here, if you think about this change in pressure here, delta P is equal to this thickness times the unit weight of water. And this has to be atmospheric. We know it has to be atmospheric. And so what we could do is we could go down this distance, which we know is the distance in the wellbore, and we come back a distance which is equal to this pressure here, which we know the unit weight of water, and we know that at this point here the pressure has to be atmospheric, and we know the pressure here is not atmospheric, so we should be able to calculate what this pressure change should be, and we can just do the calculation to be able to figure out exactly what this height would be. And if we know what this height is next to this height, then you subtract W from T and you have this height. So maybe it's a bit convoluted, but that basically is what we're doing, is we're saying that basically in the borehole the pressure here has to be the NAPL height times the thickness times gravity. Actually, yeah, okay, this is gravity. We know that in water the distance below here, this is atmospheric, which is the same as this. The distance below here to this point has to be the unit weight of this fluid times its height. So the unit weight of water times the height of this fluid. It starts off at atmospheric here, which is 0, and goes to some new magnitude here, which is this magnitude here. And across this interface, these two pressures have to be the same. You never have to derive this, you just have to use the expression. And so since these are the same, then we can just equate these, and if we equate them, we can figure out exactly what W is, because we know everything else, as a function of this measured value. And so what we find is that the thickness of the free product in our lens is actually the measured thickness in the wellbore, but reduced by some amount, which is the density of oil. I guess let's cross out non-wetting, let's cross out gasoline and put in oil. Sorry. So the density of oil, which is less than water, so this number is less than 1. And so if you multiply the thickness by some number less than 1, you get the thickness of the lens. Nothing more than that. And so now if you know what this thickness is of this lens, you know how much you have to remove if you know it covers some area of your aquifer. And so the question then is, if you suck this material out, which is the gasoline, can you take all of it out or not? And if you can't take all of it, how much would it be that you'd get out? And I know you're texting me the answer to it, and I'll expect to get it on the screen, but I don't think, we'll see if your answer is right. So it's Derek.Ellsworth on Skype. Wow, you think I'm joking. So quick, how much is, what's the volume, right? So I could ask you, but it'll take too long. So what's the amount? How much stuff can you get out of here? If you plot, for instance, your saturation of water, how much can you get out? This is the irreducible saturation of water. This is the irreducible saturation of the non-wetting. So what is it? The amount you start with is here. So this is the amount you start with in place. So it's equal to, so you start off with 1 minus the irreducible saturation of the non-wetting fluid, right? Which is the amount of NAPL you can have in the system. If you want to remove an amount, the amount you can remove is this amount here, right? So the recoverable amount is going to be equal to 1 minus the irreducible saturation of water, which is how much you started off with. You can't get this last bit out, so that's the irreducible saturation of the non-wetting phase. So that's the amount of fluid you can get out. The volume is going to be multiplied by the porosity. And if you multiply the porosity by the plan area of 1 by 1, which is just 1 by 1 if you like, meters, and the thickness. And the thickness is going to equal this height of the free product, which is this. And so hopefully that's right. 1 minus the irreducible saturation of water. Yeah, that's the volume of product. But of course, the part that you can't get out is this here. So basically the amount of free product you get per area of the aquifer is going to be this. And so now you know how to do that. And so that, if I have to stress it, is an important result. Not for exams or assignments particularly, but it's an important result to realize exactly what's going on. And so you can rationalize it with a more complicated view of what the capillary pressure versus saturation curve looks like, but why don't you go back to Feder to figure that out. All right? So that's one important outcome from this. There is in Feder a very long and involved view of exactly how you can do this calculation and get an equation much, much more complicated than this. And it's based on the idea that if you go through the vertical profile, then if you look at the saturation profile that you'd expect to see, then the saturation profile would look a bit like a bit like this, right? So this red line would be the amount of NAPL that's present. So everything to the right of this red line. So in the chimney above the oil table, you have this smear, and so it's a small percentage of saturation. It gets larger as you get to the oil table. It's almost 100%, but it's not because there's a bit of air left, air or water left in the system. And as you get to the oil table, then there's also a portion of water which is present because you're in this tension saturated zone. So the amount, so if you like, the amount of oil in the system would look like this amount here. The amount of water in the system, again, I really need some different colored materials. The amount of water in the system would be this rectangle here. And the amount of air in the system would be this dashed component. You can't get all this? Come on. Come on. Get it together. At least you're having fun. I'm having fun. And so dashed is air, stippled is NAPL, and clear is water. And so the absolute distribution of these are controlled by these plots, right? This capillary pressure versus saturation plot. And so we already know that we can represent these capillary pressure versus saturation plots by, in a different way, Brooks-Corey plots. And you may or may not remember these, but they're basically, we've gone back a long way. It's, whoops. Did we talk? Yeah, we did talk, right? Instead of representing the response like this, which is kind of what we've just looked at, we can also represent it by these straight line plots. And the utility of these is that we actually have a relationship that describes how capillary pressure and saturation are related to each other. And so if this relationship describes this plot, which really describes this plot, then you'd think that when we look at how we distribute saturation with depth in the subsurface, which is what this plot is here, then we could also represent this by a Brooks-Corey plot, which has an equation to it, both for the air and the NAPL, and for the water in the NAPL. And if you do that, then you should be able to define this distribution analytically as an equation, and that's what this 5 pages in FEDER does. It's not important for us because you get a very similar result. You can go through looking at what the saturation change with depth is, but basically it's the same idea. If you have a thickness that you measure in a borehole, you want to translate that thickness in the borehole into some distribution in the aquifer because that's what you're going to be taking out of the ground. You could do it in the very simple way that we've done it here by just looking at a thickness of product, saying this is all NAPL, and looking at what the amount would be that's in there in the first place, which is this amount, and how much of it you think you'd be able to remove, and you get a pretty good result. Or you could do it using a very complicated equation which uses these concepts, and you'd get a result that differs by, I don't know how much, maybe by 20, 30, 40%. Doesn't matter, not very much. And so you can do that. And so that's all that is. And so we won't talk about that. And so just to close out, I think the final topic in dealing with LNAPLs is the other thing that you could imagine would be not very good is that the fact you could change the smear zone. And I think it's shown very nicely in this kind of little sequence here. And that is if you have free products sitting on the water table, you have this lens that kind of covers the water table, right? It's the oil table on top, it's the water table underneath, there's a chimney which is on the lateral side. If you looked at the saturations as you go down through this column, then in the chimney it's mainly air with a bit of oil that's smeared. The water is this black stuff on this side. And so there's a little bit of water. Once you get below the water table, it's 100% water saturated, which is this region here. And so what happens if you start pumping water out of here, or you have a drought, and the water table just physically translates? So instead of being here, it drops down to here. Well, because this is all sitting here as a lens, you could imagine as it goes down, instead of this nice column that it transmitted through here, you smear it all down along where it was originally, which is this section here, where it's kind of spread out on the water table. So it's come down here and spread out. It's sitting here, and it's giving you this smeared zone. And so now the bad deal is when you get a rise in water table again, it comes up from here to sitting where it was, then the water table comes up here, but it still leaves this smeared zone, which would be pleasant at residual. And so down here, this would be now, this is water, and this would be NAPL. And so this sits at maybe 20%. And now, in this particular case, well, the water table is kind of falling to your left. And so, of course, if you looked at whatever the gradient of delta H with delta X is, and you know that Darcy's law says K over mu dH dx, which direction is the water flowing? Come on. Even if you're texting, you should be able to do that one. Right? High gradient, high pressure to low gradient. So it's flowing this way. So what it would do is it would dissolve portions of this and take it downstream. So it's really not any different from our previous example that we talked about, where we had this little box with a plug of NAPL in it. We were flowing from left to right, but it's exactly the same thing. This is flowing from this side, water, and a pristine aquifer. An aquifer with NAPL at residual, a pristine aquifer, but now that has a component which is dissolved downstream. And so basically it's starting to look exactly like our pictures of this. You can't really see it here. And yeah, it's, I guess, our pictures. We have other pictures. I'm not going to bring them up. You know exactly what the picture looks like. All right, I'm done. All right, so that's it. So assignment 2 is gratefully received. If you're submitting it online or sliding it under Taha's door, you can negotiate with him when the closing time is for that. That's between you and he. Assignment 3 is live, but you don't need to do question 2. So that's your, thank you.